voices coming over, and it means that when your microphone's picked up, it actually cuts off the presenters. Okay, I'll just share my window, my screen. And yep, Peter, I just need to be able to share my screen. So that's been disabled as a general thing.
You can't share?
No, it's coming up as host disabled participant screen sharing. So I might be able to fix that up if I just go back to the main room. I'll just try that. That might be.
Okay. Dr. Ken, you are ready to go?
Okay, excellent. I'll just go back.
Those who are here, please let me know where you're finding the challenge. Those using a phone, please check in the left upper corner of your phone. Okay. Teacher Lisa. Those using the phone, Teacher Lisa.
Yes, Mr. Kaziba.
Okay, are you using a phone?
Window, come in and our presentation and for today's lesson is going to be based on energy. But what I thought I might do first up is just give a general introduction about myself, and we'll work from there. Well, my name is Ken Silburn and I live in Sydney, Australia. So, so you can see Australia there, and it's amazing. It takes up so much of the space of the world, but most of it in the centre, there's no one lives there. And in particular, if I wanted to specify exactly where I live, it's sort of, I don't know if you can see my cursor, or the arrow, but I live near Sydney and just about 30 kilometres away from the main city. But what is amazing about today is it doesn't matter where you are in the world, you can communicate to other people. And I find that's absolutely amazing. So a bit of an advertisement for Sydney. We've got the Sydney Opera House, you may have heard of, the Sydney Harbour Bridge, and that's me. And I do have a red motorbike, and the reason being is red motorbikes go faster. So we'll have to do a test on that. And why would I be in STEM? In fact, why would you guys for your holidays be in STEM? Okay. I promote STEM because I believe that we need heroes. And at the moment, of things like global conflict, which I suppose science won't be able to help, but with things like global warming, I apologize because it's my generation, my parents' generation that have caused global warming. So we're going to be looking forward to having people that will solve the problem. And that's where it'll be students of today. So imagine yourself in 10, 15, 20 years, what will you be doing, or what will you have done to save our planet? Now, if you'd like to use the chat, I said that we do need some heroes. This is my hero, and I'd wonder if anybody would like to guess who he is. So I'm just opening up the chat. Okay. Do we have any guesses?
Neil Armstrong.
Well, actually, a good guess, because Neil Armstrong is probably the first person that I would think of. However, he isn't, he's not American. So at the moment, if we're out there, if you're Googling away, he's a famous, or he's not an astronaut because he's from a different country. What country would that be? I'm not quite sure if our chat's available, but let me just jump back here. Oh, good, we've got our chat. Okay, right, okay. Well, actually, Aris, you guessed Yuri Gagarin, very, very close. Okay, I'll tell you his first name is Alexi. No more takers so far. Okay. I'll give you another clue, and if you're on the internet, which obviously we are, if you want to Google this, he was one of the first Russians to do something to do with space. And we sometimes call it walking. All right, let's try and do this Google search. So he was the first Russian cosmonaut to do walking in space. We should work out a prize for the person that finds out his name. Okay, I'm going to leave. I'm not going to tell you what his name was, but well, I won't tell you his surname. Put it that way. Okay, Alexi was yeah. Well, actually, when someone finds his surname and gets back to it us in the chat, then I'll tell you the story as to why he's my hero. What you might like to do though, can you share with us who your hero would be? Do you have a hero? Do you have a hero like it's a superstar, someone in the family that's your hero? Can you just share that in the chat with us? Oh, hey, who said Alexi Leonov? That was Ruth. Ruth, can you actually jump or open up your mic?
Yes.
And you have to tell us why he was so important. Heroic deed. Okay, so we've got it was Alexi Leonov, and that was Ruth that actually found that out. So Ruth, can you just tell us more about what he did?
He was on that day in 1965. Alexei Leonov became the first human to walk in space. He floated for 12 minutes and 9 seconds before returning to his destination where he was moving as an astrologer.
Okay, thanks, Ruth. Okay, so Alexi was the first man or the first person to walk in space. And I'll come back hopefully at the end of the lesson and I'll tell you about why I think he was just so super, super cool. Okay, but let's get back onto our lesson because that's why we're here. So I'm just going to share my screen again. Okay, so what we need to have is a good definition for work. So energy is the ability to do work. So any question that you're asked in an exam, anything to do with energy, okay, we've got a candle, okay, that candle's burning and that flame has got the ability to do work. It can heat up something, it can light up something, so we can. Now, there's lots of different ways that we can talk about energy when we talk about forms of energy. And I want to show you a simulation, and I've placed here on the screen the website to go to it. You don't have to go to it now, but you might like to go and play with this later. But I'll just show you a little bit about it at the moment. Let me go to, so I have to just. Okay. This simulation is made by FET, and that's out of Colorado. So I'm just going to click on the intro, and let's have a look at data. I'm going to drag it up, and I don't want to put it right to the top because that's a bit dangerous. I'm just going to put it here and let her go. So, okay, probably that's what we expect, that she's just going to keep on going up and down, up and down, up and down. But is that really what happens? Let me just stop sharing, and in the chat, can you write down, please, what it is that would stop her from going up and down, up and down, up and down? Okay, I'm sure she'll get very bored if she's going straight up and down. Hey, friction, good. Okay, that's Mitch and Tessa. Thank you. Okay, so friction is going to slow her down. But I'm going to jump back to that because I think it's quite cool. And let's see if we can do some more playing with this simulation. Now, if we forget about friction at the moment, because friction on here, those settings, and I can make it so that she does slow down. But let's not have, make it nice and easy for us. Okay, I'm going to put it back up to the top, and I'm going to click on the speed. So her speed is changing. So whereabouts is she traveling the fastest? Can we put that in the chat, please? Okay, is she traveling the fastest at the top or at the bottom? Okay, just put your answers in the chat. Okay, I'll give you a few more seconds to there. Okay, we've got Tessa, okay. Super fast Tessa at the bottom, yes. Bottom. Okay, we've got someone out for the top. Okay. So let's analyze this. She's going, when she gets to the top, she's stopping and she's turning around. Let's have a look and see if we can actually measure about her speed. So I'm going to click on here. I'm going to put something to measure her energy level. Let's put it back up again and swing. Okay, so when she goes past this point, okay, her speed is 2.13 meters per second. But let's look at the energy. The kinetic energy, 198, 200. Potential energy, wow, the potential energy is quite high. And look at the total amount of energy. So the total amount of energy is 2,866.7 joules. What's going to happen if I move that scope towards the bottom? Look at a few things. What's going to happen to the kinetic energy? Can we type into the chat there that it will increase? Mick, thank you. Even if somebody else has already got the correct answer. Okay, so we've said everybody there is saying, yep, it increases. Well, the potential energy due to gravitation, I think we would guess that that's going to decrease. But what happens to the total? What happens to the total amount of energy? Okay, type in your answer. At the bottom here, let's put it right down at the bottom. Let's put the total we're looking at. Oh, she doesn't get that high to here. 2,866.7. So what we can actually work out is our total energy isn't going to change, it's going to stay the same. But in this example, we're going to be changing backwards and forwards from potential to kinetic energy. Okay, let's jump forward. And we'll send everybody the link to this. I think you can have a copy of the PowerPoint presentation. But if you vet simulation, you'll come up with hundreds of different really good science simulations that you can play. Okay. Forms of energy. Now, we just looked at mechanical energy, so we looked at kinetic and potential energy, and we quite often just call it potential energy, but potential energy due to gravitation. So you might like to equals 1/2 mv squared. Now, can anybody tell me what, or can everybody tell me what does the V stand for? Yep, velocity, good, velocity, excellent. Okay. Katie, yes, maybe velocity. So velocity is, it's speed, but in one direction. So it's to do with move. So what's the H? Good. Now, there's other types of potential energy. If I have a spring and I stretch it, then that's going to be, we call that elastic potential energy. Or with a rubber ball, if I squeeze a rubber ball. Now I'm telling you that because it's going to come up in the quiz later on. Okay. The other forms of energy we've got electrical energy, chemical energy, light energy, and sound. Now, this is one thing you have to be able to remember, and this is the conservation of energy. So we can't destroy energy, it's always there, but we can change it from one form to another. So think about if I turn on a light switch, what is our change? What are we changing as our form of energy? Please put that in the chat. Good. Okay, now, in fact, if a light bulb, it'd be a really good thing to do if it's been on for a while. Probably not, because what else is when we flick the switch? We've got light energy. We've also got, oh yes, Tessa. Hey Tessa, I'm quite impressed there. Tessa's came up with chemical to electric to heat, then light. Okay, maybe. Well, one of the things about lighting, and this has really changed the way which we work now. Light bulbs, if you went back maybe say 10 years ago, light bulbs would actually produce a lot of heat. So that was a waste of energy. So now when we've got LEDs, they don't produce that much heat. They produce a lot of light. So that's better for our consumption of energy. So if we flick the switch on the electric switch, we get light and we get heat energy. Another example, if you're driving a car, what is our form of energy that we use to power the car? Yes, okay. Good, we've got it changing into mechanical. So if I start up the car, I start up the motorbike. Katie actually said also about using electrical energy. One of the things that we have, when I start up the car, I'm burning petrol. So I'm using chemical energy and I'm changing that into heat energy, and then that will actually operate the car. Now, we've had a few people that have came up in the chat and said about, I mean, Quentin has said some cars use solar energy, some use electrical energy. Okay, we've had a few people there that just said about the volume. I hope the volume's actually okay from your side. Okay, can I just have a show of hands if you can hear okay with the volume? good. Yep, Gilbert and Tessa. Okay. Yep, show of hands if you can hear me okay. Good, okay. It's always frustrating if you're giving a presentation and no one can hear you. Okay, good, let's go back. I think it was Ruth that said about solar energy in the chat, but one thing that we have to really work on as a world is being able to produce energy, and we have to know the difference between renewable energy and non-renewable energy. Okay, I think it's obvious that renewable is things that we can actually reproduce. What are some forms of renewable energy? Can we go to the chat for that, please? Okay, good. Sorry, it just took me a while to get back onto our chat there. So Gilbert has actually said about wind energy, and you can see that in the slide. Yep, so we've got turbines, we've got solar energy, solar, wind, hydro. Yes, hydroelectricity. Do you use hydroelectricity in Uganda? I know we do it in Australia. Geothermal energy. Thanks, Ruth. Masazi has mentioned biomass from plants. Now Gilbert has actually put in nuclear energy. Yes, that is. I'm not quite sure whether nuclear energy, whether that's classified as renewable or non-renewable. I might ask Stephen if you could jump in at any point. I'm just wondering, nuclear, would that fit into being renewable or non-renewable? I think I agree there. I think I'd have to agree with Ruth. Nuclear energy is non-renewable because we use it and then it's used up. It's something that we can't go and reproduce. Okay, good. I'm impressed. Okay. For high school, we talk about our source of energy on Earth is the sun. So if you think about all the way that plants produce food, okay, it all comes from the sun. Now, we're going to have a bit of a quiz, and we're going to do what's called a Kahoot. So that means you're going to have to not leave, you don't have to actually leave the Zoom meeting, just open up another window in whatever you use to go with the internet. And I'll give you, if you go to www.kahoot.it, and I'll put up the code that you have to put in to join our quiz. Okay, let me just do that. Okay, so if you could enter when you get to it, enter the PIN. And if I could ask you just to use your first name. Well done, Tessa. Okay, we've got Mariam. Okay, so in order to join, you need to go to either Google Chrome or Firefox or whatever Safari, whatever you're using for to browse the internet, and to go to www.kahoot.it, Or if you just Google Kahoot and go to where it says play. Okay, Akunda's asking, what is the game pin? It's 205460. Okay, so we've got here 1, 2, 3, 4, 5, 6 players. What we might do is we'll just wait for another 4. Great. Thanks, Natalie. 1, 2, 3, 4, 5, 6, 7. Let's make it so we've got a good competition. So we've got 3 more people. So if you can jump online to Kahoot.
Yes, I say
Oh,
bye.
1, 2, 3, 4, 5, 6, 7, 8. Okay, you can join at any time. So let's start. I'll just explain about Kahoot. Okay, Kahoot, you will get the question will come up and you'll have 20 seconds to answer the question, and you just click on the colored button for it. Okay, so let's go. Now, I wonder if we remember about okay, Macy's coming first. Good, a girl swinging on a swing the same as a pendulum. Oh, well done, that was good. Okay, Macy's back in the lead. Okay. Hey, yeah, I suppose we could say it disappears, but remember about energy that it doesn't, we can't create or destroy it. We can change the form.
What was in here? I'm going to say.
Okay, and we're going to go up to 10. So we've got 2 more. Oh, awesome. Okay, most of us got that one. That was probably, I thought, a difficult question because energy or electrical energy is the movement of charged particles or electrons. Alice is right still at the top, and we've got 2 more questions. Good, good. Okay, so it's electricity going to light and heat. Okay, this is our last question. So we've still got people involved that can get to the top 3. Let's have a look. Okay. Now, that was actually, I apologize, that was a bad question. So let's do one more question. And then we'll go back. Okay, great. I didn't use that term electromagnetic, but when we talk about light, light is also called electromagnetic energy. Okay, let me see who was our winner. Let's write down Paris, second Tessa, Natalie. Macy and okay, well done. Okay, and okay, good. Our definition right from the word go, and we have to remember this one is energy is the ability to do work. Okay. Awesome. Okay, let me just get back to our screen. There we are. Now, just so I can know who our winners are, Aris. Is Aris there? Aris, can you tell us what school you go to?
Pardon?
Yep. What school do you go to, Aris?
What?
Pardon?
Yep, Aris, can you tell me what school you go to?
Mango Senior School.
Right.
I go to senior.
Okay. Awesome. Well done. And Tessa. Where's Tessa?
Yes. Yes.
Tessa, what school do you go to?
We're Anyanji Girls Secondary.
Good. And Natalie. You're top. You are third place getter. What was yours? What school do you go to? Natalie.
Yeah.
What school do you go to?
Iganga SA.
I think we've our fourth place was maybe. Okay. Let's see, Macy, our list here. Okay, and what school are you from?
I go to Iganga Secondary School.
Oh, the same as Natalie. Oh, that's good. Okay. Well done. Now, just go back here. Peter, that's all that I wanted to go through. Although I did say I was going to talk about Alexi Leonov and tell you about his story. Okay, is that okay if I do that for about 4 minutes? Can I have a hands up if that's okay? So I've got a few people that are saying that's okay to talk about. Great, okay. Well, Alexi is my hero because I just think he was super cool. So if you could imagine being the first person to leave a spacecraft, but a lot of people don't know the full story that happened, because when he left the spacecraft, he was traveling at about 50, or I think it was about 30,000 kilometers per hour. So extremely fast. But he didn't have any of that wind resistance that we have if you put your hand outside of a car. But when he left, his spacesuit, because of the change in pressure, actually started to expand. And it expanded so much that where he had his hands in gloves, that actually didn't happen anymore. So he was basically inside this great big suit. And the problem, he couldn't fit into the porthole that he actually left. And all of the Russians that were back talking to him were basically saying that, congratulations, you will go down in history as being the first man to walk in space. And in fact, they actually thought he would have been the first man to have died in space, because they couldn't think of a way to get him back in. And being super cool, he actually found a way that he could actually release the air from the inside of his spacesuit. So it was enough so he could actually get back inside. He actually was very sick. He ended up getting the bends from it. But I just think, how cool would you be to be able to be in that position and solve the problem? That's why he's one of my heroes. Okay. Peter, is there anything else that we need to go through? Just looking at the time there.
Dr. Ken, I thank you so much for the wonderful presentation that you have given us today about energy. Maybe this holiday we are running on the theme, which is the waste management. Anything like a project or something that you can share with us that can relate energy to waste management in our communities, we'll be thankful if there is any.
Look, one thing that amazes me, and let's do this and find how much people know about space. So just get ready to go into the chat for this. Okay. So, what was the first country to actually go to the moon? Okay, so if you know the answer, just type it in. So we're just zapping straight onto the chat. Okay, good. Okay. Well, we've got Soviet and Russia. Well, the first country to get to the moon was the US. So the first person to go on, and we had this, somebody suggested it was Neil Armstrong was the first man to go to the moon. Now, let's use Google and tell me, how long did it take to get to the moon? And in fact, get just a little bit closer to the microphone here so we can hear. Okay, so waiting, we need someone to, yeah, 3 days, thanks Tessa. So yeah, 2.5, 3 days to get to the moon. Okay, now think about that. If you're in a very, very small spacecraft and you're almost lying down for most of the trip, sort of lying down, sitting down, you'd have to be really good friends with the people beside you, because you have and the formula for this, actually we should know the formula for this one, but kinetic energy equals 1/2 m squared. Okay, Mitch, I've got it down that you do have a question, so we'll come back to you in a moment.
Yes, sir. In the formula finding the potential energy, we gave us the formula as mass times grams times height. So is it a must for you to be grams, or you can also put kilograms?
It's mass in kilograms times the acceleration due to gravity, which is, that's what the G is, and times the height in meters.
Okay.
Okay, now we've got a few questions coming up about the formula. Okay, so the formula is, I'll put it in here. Okay, kinetic energy equals 1/2 m v squared. Oops, wrong way. Okay, and just going back to the chat. Okay, we've got, I think it was Tessa that came in first with the correct answer. Okay, which was 16 joules. Okay, let's go back to our first question. So we had this, the stone mass 8 kilograms is lifted through a height of 2 meters. So the formula for that was potential energy equals mgh. Now, we found the answer to that. I hope I've got this right. Was it 160 joules? Now, if we lifted up that brick, or sorry, that stone to that height, and then we dropped it, what speed would it actually hit the ground? Or in fact, let's make that question a little bit easier. What would be the kinetic energy as it hit the ground? Let's put your answer into the chat, please. Okay. Now we've got Gilbert Rex. Okay, I'm going to type the question in so we've all got it, because a few people are not working with the volume. Okay, I'm just going to stop sharing. I just want to get Gilbert, if you can unmute for me, and I'll get you to. Okay.
Yes, please.
Yep. Hi, Gilbert. Your answer, you gave 160 joules for the kinetic energy. How did you get that?
The kinetic energy.
Yes.
It was mgh.
Good. Okay.
Meters times grams times height.
Good. So when we've lifted the stone up and we've got it to the height, we've given it 160 joules of energy. Okay, well done. Okay, so we've got that. And then when we've let go, that potential energy is changed into kinetic energy. So just before it hits the ground, it will have kinetic energy of 160 joules, and its potential energy will be 0. Okay.
Yes.
Good. So I'm going to pose to everybody. If we now know that the kinetic energy is 160 joules, can we work out how fast it is traveling? Because that's the velocity. Velocity is the speed that it's traveling at. Okay, so let's find that for us, please. I'll just put this back for us, everyone, so everyone has the same question. Okay, once again, please put your answer in the chat. Okay, and just to give people a bit of a clue here, I'm just going to our formula that we're using for kinetic energy was kinetic energy equals 1/2 mv squared. Okay, so v is velocity, or the speed that it is traveling. Okay, I'm just going to go through this one with us. Okay, if we remember our formula, kinetic energy equals 1/2 mv squared. we worked out that our potential energy for the maximum height was 160 joules. Okay, so that is what we're going to have as our energy that's going to be converted into kinetic energy. So that is going to equal 1/2 times, what was the mass? 8 kilograms, good, thank you, times V squared. Now, oops, I'll just break that into it. So, let's solve this for V squared. So we're going to have 160 divided by 1/2. Just trying to put this as. So if we give the 1/2 8 to the other side, so we're going to have 40 V squared. So my equal sign doesn't want to work properly there. So V is going to be the square root of 40. Okay, now I'm just going to go back to our window. Oh, actually, can I just say, well done, I wasn't chat, Elijah. Okay, and Tessa, good. In fact, if I just go back, I want to show here. So if you remember this when we're talking about kinetic energy, in the question that we just did, we had 160 joules of energy when we went to the top, and then when we let go and that stone falls, that potential energy is changed into kinetic energy. Okay, I'll just jump out. Now there was some questions we had. Mitch, you had a question, and Ruth just had her hand up too. Sorry, so Mitch. Okay, no question. Okay, Ruth, your question?
My question is, for number one, you added us other parts to answer you first gave us to find the potential energy the stone develops, and then our answer is 160 joules. Then you asked us again to find its kinetic energy before it dropped down. And to find the kinetic energy, we need to have the velocity. So which velocity did we use to find the kinetic energy before it dropped?
Right, well, if we're holding it still, and we've raised it to the top, then its kinetic energy is going to be 0. And when we drop it and it starts to move, when it hits, or just before it hits the ground, its potential energy will be 0 and its kinetic energy will be what it was before as its potential energy. So it would be that 160.
So they are technically equal, almost.
What happens is we change, because wish I had a drawing tablet I could use with this computer for you, but when we're at the top, that potential energy is there. When we let go, that potential energy is changed into kinetic energy. Okay, let me just move on to it was Tessa, and then I'll hand back to Peter. There we are, Tessa.
Okay, thank you so
much. On the other calculation, we got v squared is equal to 40. Do we leave it like that, or do we find the square root?
Look, if you could find the square root, that would be much better.
Thank you.
Thank you. Tessa, you had your hand up.
I've just finished the question and you answered.
Okay, well done. You've actually worked well today, Tessa. That's quite good. Peter, I'll pass back to you there.
Okay, Doctor, thank you so much for the wonderful time you have given us today. The presentations were so wonderful, and I think you loved the class. The quiz and everything that took place was so good for us. I'm going to ask Ruth to give us a vote of thanks and then a closing prayer, because Dr. our time is up now. We have used all our 2 hours well. So Ruth, you give us a vote of thanks. Thank Dr. Ken for the wonderful lesson, and then you will give us a closing prayer and we'll stop our lesson soon. Thank you.
Okay, thank you, Teacher Peter. I'd like to thank Dr. Ken for the guidance through the topic of energy. Well, personally, I've been able to discover something new, and that it was through energy that this Alexi Leonov was able to also move in space, which was a sort of illustration, but a fact, which added on to the knowledge of energy, and then the different games that can be played, like simulation, energy skate park, and the rest, to exercise us and to keep enabling us understand this concept of energy. We've also been able to learn in kinetic energy, the calculations, the formulas, and all the rest that will help us. So, vote of thanks to Teacher Peter for that idea of conserving our environment using energy conservation.
Terrific. Can I thank you, and can I thank the students?
Sorry, I think we can pray.
Ruth.
Yes, Ruth, please go on with the prayer. Sorry.
Pardon? Okay, let me pray. Father Lord, we thank you for this day. Thank you for the gift of life. We thank you for guiding us and shielding us. We ask that you may lead us and enable us go through the remaining part of the day and still be able to learn something new each day of our lives. We bless you for all that you have done and what you are in our lives, and we honor you of in Jesus' name we pray. Amen.
Thank you. Can I have a big thank you to the students, because I do know it is difficult when you're listening to someone that has a totally different accent. So so thank you for putting up with the Australian accent for that.
I think we should feel free to leave or return to the main session for further information.
Good, thank you.
A good evening to you all.
Ruth, for the wonderful prayer. Doctor, anything before we go?
No, I'm just thank you, and I look forward to eventually getting back to Uganda so I can meet people personally. It's been Peter, you might remember it was 3 years ago, and I keep on planning to go back. However, COVID has